Welcome to our discussion on the normal distribution. You can see that our objective here is to use the normal distribution to be able to determine probabilities as z-scores. And this will help us see kind of a better picture of the way our data is dispersed or spread out. In many instances, the shape of our data falls into one of very few recognizable forms. For instance, if we look at a large sample of heights, men's heights or women's heights, doesn't matter which, a histogram built with that data would look symmetrical and approximately bell-shaped. And really, with a large enough sample, our histogram would become what we call a completely normal distribution. And normal distributions occur a lot with data, but more importantly than that, you'll learn later on with the central limit theorem that even if your population isn't normally distributed, if you sample from it, the sample distribution that you create is always normally distributed. So the normal distribution becomes very important for you to understand, because basically all of inferential statistics are built on the concept of what a normal distribution is, what it looks like, what its properties are, and how to use it to calculate things. So the characteristics of a normal distribution is that it's bell-shaped, meaning that it has one mode, right? It's got one bump in the middle, and it's symmetrical. The mean, median, and mode are all the same, and they're right in the middle where the highest point of the curve is. So for instance, let's just draw one so we know what we're talking about. So here is a typical bell curve. Excuse my lack of drawing skills. Okay, right here in the middle is your mean, also your median, and also your mode. You can see it's the mode because it's the tallest point, remember, and the height represents frequencies. So this is the most frequent thing, so that's the mode. It's the median because it's symmetrical, which means we have exactly 50% of our data below it and exactly 50% of our data above it, right? So that makes the median. And then it's the mean because it's symmetrical, every value we have, we have this frequency of this value, this exact same frequency of this value. This is the same amount above as it is below, so they offset each other and they average to the middle, right? So everything averages the middle. So there you go. Mean, median, mode are all right in the middle. The total area under the curve is always set equal to 1. That's why we have 50% in one and 50% in the other, so we can talk about 0.5 and 0.5 as being its area. And it's completely defined by its mean and standard deviation. So every normal curve can be designated by what its mean is and what its standard deviation is, because all that's going to happen is the mean is going to shift it left and right on the number line, right? So for instance, if this has a mean of 100, we're out here at 100 on the number line. But if we have something with a mean of 25, it's down over here at 25. And if we have a big standard deviation, it's going to be wide. And if we have a small standard deviation, it's going to be narrower like this. It's going to be taller and narrow because the area still has to be 1, right? So technically, if it's this narrow, it should have been taller. And again, excuse my lack of drawing skills, but you get the idea. Okay, a z-score it literally is how many standard deviations you are from the mean. So a z-score just tells you the distance your data value is from the mean in standard deviations. Think of it as like a unit of measure. You can say you're 3 feet from something. You can say you're 2 meters from something. You can say you're 6 inches from something, right? Those are all units of measure. Well, you can say you're 1.5 standard deviations away from something. It's a unit of measure. So that's what it is. A z-score is just how far you are from the mean in terms of standard deviations. If we're talking about a population of things, and of course we're using mu and sigma, right, because population is Greek letters, and we get a z-score of this. If we're doing a sample, you can see we have x bar and s. Same formula. It's just whether we have a sample or a population. So given that the mean is 159.5, standard deviation is 7.1, we can now calculate all of these z-scores. Very simply, the z-score of the first one is just going to be 148.2 minus the mean divided by the standard deviation. And we would do those over and over. Now you can see right here, this is going to give us a negative number. A negative z-score tells you that you're that many standard deviations below the mean. right? Because 148 is smaller than the mean. That's why we take the number minus the mean and we don't do the mean minus the number. Okay, so as we saw in our first example, we get a negative 1.59. So that means 148.2 is 1.59 standard deviations below the mean. Now you might be asking yourself, well, why do we care that it's 1.59 standard deviations rather than just saying it's 11.3 centimeters right below? Well, because the reason why we do this is so that we can compare two different sets of data. So this data is heights of Canadian women, and it's in centimeters. And so somebody who is 148.2 centimeters tall is considered 1.59 standard deviations below the mean. Now, let's say we went and calculated the heights of American women. They're going to be roughly the same. They're also going to be normally distributed. But the mean and standard deviation are going to be different for one reason, because we're going to measure in inches instead of centimeters. So then we're going to come along and we're going to say, okay, this woman is, so many inches tall. What is that as a z-score? We calculate her z-score, and we get a z-score of negative 1.59. We go, these two women are relatively the same, even, because they're both 1.59 standard deviations below the mean. Or we calculate it, and, the U.S. woman is, positive 1.59 or positive 2. And we go, okay, well, now we know she's a lot taller because she's 2 whole standard deviations above the mean, whereas this other woman was 1.59 standard deviations below the mean. So it enables us to compare two sets of data that might be on two different measurement scales, i.e. inches and centimeters, that kind of thing. Now, of course, you could just convert inches to centimeters or centimeters to inches and make your comparisons more directly, but you can't always compare units of measure. I'm sure you guys have all heard about the SATs and the ACTs, right, as those entrance exams to get into college. Well, the SATs, they keep changing it. It used to be based on 1,800 points, then it went to 2,400 points, and I think it went back down to 1,800 points. Heck, I think it was even 1,200 points at one point. The ACT, I think, was always based on like 34 points, 36 points, 32, somewhere around there. So when a student, applied to a college and they had an ACT score and a different student had an SAT score, how the heck could a college compare those and figure out who did better? Well, they would do it with z-scores. So they would take that SAT, raw score, and they would convert it to a z-score, and they would do the same thing with the ACT score. So if you had a 1.2 z-score on your SAT, that means you were 1.2 standard deviations above the mean on your test. And so if the ACT score had a z-score of 1.3, that means they did better because they were 1.3 standard deviations above their mean, right? So they were further up the curve than the other student. And that's how you can compare two different sets of data with two different units of measure. That's why we deal with z-scores. Okay, for our second example, right, we do the same thing, 160.3 minus the mean divided by standard deviation. They're 0.11 standard deviations above. Last one, we do the same thing. And, the first thing we'd have to do is we'd have to convert this into centimeters because, it's in centimeters. So 1.7 meters times 100 gives us centimeters. So we get 170 centimeters. Then we subtract the mean. Then we divide, and we get 1.48 standard deviations above the mean. It's just that simple. Now, as we said, the mean and the standard deviation just determines where it is on the number line. If you take it and you convert everything to, so basically take every number and you divide by the mean, take every number and you subtract the mean from it, this now becomes 0, and then divide everything by the standard deviations, this distance becomes 1 and 1, and you get what's called the standard normal curve. And the standard normal curve is just the z-scores that correspond to the raw data. So sometimes you can convert things into z-scores in order to figure out percentages, but you don't always have to do that, and I'll show you why in a second. So see if you can answer this one. Calculate the z-score for this scenario. You should have gotten 0.68. Okay, suppose the average caloric intake for a woman is 2,050 calories per day with a standard deviation of 175. If we assume that caloric intake follows a normal distribution, which it pretty much does, find the percentage of females in your class that consume more than 2,000. Well, that's easy. Just do the z-score for 2,000, get negative 0.29. And then we have to figure out how much area is above that, right? Because basically, I always tell my students, draw pictures so you can see what the hell's going on. Here's my curve, right? Here's my middle at 0. We're down here at negative 0.29. And we want to know the students that ate more than, right? Consume more than. So we're looking for all of this area. We know it's at least bigger than 50 because remember the mean is right in the middle, so that's 50%. And we got to figure out how much that is. Well, different forms of technology will give you this. If you use the TI calculator, it's pretty simple. You can do the normal CDF function. And what the normal CDF function does is it's a cumulative density function. That's what the C and the D stand for, cumulative density. So it adds up the area from the low end to the high end. So if you want to know how much is above negative 0.29, you need to make that your low end, right? So you've got to put in negative 0.29. And then your upper end needs to be a really big number. They show the example of 1e to the 99. I just put in a bunch of 9s. Okay. And then we're dealing with z-scores. So the mean of our z-scores is always 0. The standard deviation is always 1. We throw that into the formula, and it gives us 0.614, which you can see is exactly what they did when they rounded to 2. Now here is a nice little thing that these calculators do. You don't have to convert them to z-scores. You can go back to just the raw data. Because you'll notice in that formula, it asked us for the mean and standard deviation. It defaulted to 0 and 1. So if we go over here to our second vars, which is our distribution menu, and we go down to normal CDF and enter, instead of the lower end being the z-score, we can just let the lower end be the 2000. The upper end is still going to be a bunch of 9s, but now the mean is the mean of our sample, 2050. And the standard deviation is the standard deviation of our sample. We paste that into the formula, and we run that, and look, we get the exact same thing, roughly, right? The reason why it's different is negative 0.29 was a rounded answer for the z-score, whereas when we ran it this way, we got a more precise answer because we weren't rounding our z-score. So just keep that in mind, that you can just do it directly by putting in the numbers rather than converting to a z-score first. And that's it.